Hello everyone, my name is Ingmar Schubert. I am from the Learning and Intelligent Systems Lab at TU Berlin, and I am going to present our work Learning to Execute Efficient Learning of Plan Condition Policies in Robotics here at NeurIPS 2021. This work starts from the observation that model-free reinforcement learning and planning have complementary strengths and weaknesses. While for reinforcement learning, no prior knowledge of the environment is needed, and if given enough time and resources, the optimal policy will in principle always be found. Model-based planning requires a model of the environment first, and if this model does in some way not accurately account for stochasticity in the real world, or maybe also contain systematic errors, the resulting policy will not be successful. On the other hand, while reinforcement learning finds the optimal policy in principle, in practice, this often requires prohibitive amounts of data or compute resources, and model-based planning in general offers a much more efficient way to reason about the agent's interaction with the world. Since in many interesting cases in robotics, a rough model of the environment is readily available, it therefore seems natural to try and integrate both approaches into one framework that combines the advantages of both. Learning to execute, or L2E, offers a novel perspective on how this can be done, namely by learning a policy that can execute plans. A goal-conditioned Markov decision process, or MDP, is an MDP where the reward is not only a function of state, action, and next state, but also a function of the goal that the agent intends to achieve. Therefore, a reinforcement learning agent navigating a goal-conditioned MDP needs to learn an optimal policy that is also conditioned on the goal that it wants to reach. The L2E agent does not learn a goal-conditioned policy, but it, in contrast, learns a plan-conditioned policy. In a plan-conditioned MDP, the reward function does not only depend on the goal, but it depends on an entire plan leading towards that goal. This plan can describe a model-based planner's approximate idea of how to reach a goal from some initial state. L2E integrates reinforcement learning and planning by learning a policy that executes plans, and therefore the L2E policy is not conditioned on a goal, but it is conditioned on entire plans. We construct a plan-conditioned MDP by combining a goal-conditioned MDP with a model-based planner. In our case, a model-based planner is modeled as a distribution over plans, which is conditioned on some initial state and the goal. Importantly, the planner can create multiple possible plans leading from the same initial state to the same goal. We use final volume reward shaping, or FVRS, to create a plan-dependent reward function from a goal-dependent reward function. This plan-dependent function rewards staying close to the plan and rewards advancing towards the goal along the plan. In contrast to potential-based reward shaping, FVRS does not leave the optimal policy invariant, and therefore the optimal policy for a given goal in general will be different from the optimal policy for any of the plans that lead to the same goal. In general, the space of goals of a goal-conditioned MDP is much smaller than the space of plans from the plan-conditioned MDP that can be constructed from it. Therefore, the plans that we collect during learning are buffered by the L2E agent, and each experience trajectory is then relabeled with respect to multiple plans that are sampled from this buffer. How this plan sampling is done in detail is an important design choice, and here we compare sampling plans uniformly and sampling plans such that plans with respect to which the experience trajectory has higher reward are sampled with higher probability as well. We find in our experiments that using this kind of reward-biased replay greatly improves sample efficiency. In the experiments, we consider two different robotic manipulation environments, which are shown here. In the basic pushing environment on the left, the agent controls the 3D velocity of the spherical end effector and is tasked with pushing the box towards the green goal. The blue pipe indicates the end effector trajectory as it was planned by a very simple planner. And this planner also plans for the intended box positions, but these are not shown in these visualizations here. In the obstacle pushing environment on the right, this task is complicated by an additional obstacle in the middle of the table that the agent has to navigate around. And importantly, the agent does not learn to follow the plan in every detail. For example, as you can see, it is planned that the end effector reestablishes the contact with the box to push it around corners. But the L2E agent learns to push around corners in a smooth movement. If the planner provides multiple plans for reaching the same goal, the L2E agent can learn to follow each of them separately. This is in contrast to goal condition policy, where the optimal behavior is only dependent on the goal and not the plan leading towards that goal. And it has the advantage that the L2E agent can generalize to new environments if the planner is slightly modified. So for example, in the example shown here, if the obstacle would be moved to the left, the planner could account for this by only suggesting plans that go around the obstacle on the right side, and therefore allowing the L2E agent to still succeed in this changed environment. We compare against baselines that either purely rely on planning or are pure reinforcement learning methods like hindsight experience replay. And we also compare against other approaches that combine learning and planning. These include learning an inverse model before executing the plan and using the plan to obtain subgoals that are then navigated by the reinforcement learning agent. L2E can also be categorized as a method that combines learning and planning. And these two baselines, which combine planning and learning in L2E, kind of lie on a continuum, which goes from following the plan very closely with an inverse model to following it loosely as is done in L2E. Using reinforcement learning to reach planned subgoals can be seen as a middle ground here. In both environments, we find that L2E significantly outperforms the baselines. In the obstacle example, plan execution with an inverse model is more successful if very little data is available, but L2E can improve on this baseline if given enough data. The lines in these plots are averaged over multiple independently trained agents and also multiple random initial configurations for each test. The shaded areas then indicate the corresponding confidence intervals. To recap, we introduce L2E, which combines reinforcement learning and model-based planning. L2E uses FVRS, or final volume reward shaping, to translate goal-conditioned MDPs into plan-conditioned MDPs, and then learns plan-conditioned policies for them. L2E in our experiments outperforms baselines that are purely planning or purely RL-based, and it also outperforms other baselines that combine learning and planning. Thanks for listening, and I would be glad to chat with you at our poster.